because today we have a back-to-back. We have two of our PhD students. We have first Layla, who is a homegrown success, supervised by Tim and Angela, as you can see. So yeah, without further ado, introduce Layla.
Yeah, thank you, and thanks all my fellow PhD students come to support as well. That's so nice to see so many of you. So yeah, I'm working with Tim and Angela on solving PDEs, using numerical methods. So yeah, maybe this is a bit basic, but actually there's other mathematicians here not applied. So many problems that require mathematical modelling can be described using PDEs, and solutions to these problems are really important in science and engineering and beyond. I'm trying to move that. Okay, yeah, that's better. Just trying to move it away. Yes, however, many PDEs don't have analytical solutions, and so they can't be solved using typical analytical methods such as separation of variables, method of characteristics, or the use of Green's functions. And so that's where it's really useful to use these numerical methods to solve them. So in my work, we particularly look at an algorithm called PGD, which I'll introduce in a moment, and we're just solving some well-known problems like the Poisson problem, convection diffusion problem, and the Stokes problem. Where do I go? Yeah. Okay, so the PGD stands for Proper Generalised Decomposition, and this is a numerical method based on a dynamic construction of the basis functions. And it achieves the approximation by computing a separated series approximation using enrichments of the basis. So at each enrichment, an alternating direction fixed point algorithm is used to determine the coefficients. And this alternating direction iteration procedure, or AGI procedure, works by assuming an initial guess for y and then using that to solve for x, and back and forth until a fixed point is reached within a certain tolerance. So like other numerical methods, we define a mesh-based discretization of the domain, and the problem can be solved at the nodes generated by using basis functions, for example, using the finite element method. So yeah, we can see on the right, we've got the approximation given in terms of basis functions phi, and we can see the separated representation over the J enrichments. So I first used the PGD along with the finite element method to solve some PDEs. So finite element methods are local methods where the discrete problem is formulated using local approximations to derivatives. And of course, increasing the number of grid points improves the accuracy of the solution. So I've got the Poisson problem here, and it's an example. We've got the exact solution U and source term F. And in the middle, we've got the approximation. And you can see on the sides the 1D approximations for each enrichment shown. And then on the right, I've just got a figure of the errors. So that's the difference between the exact and approximate solution, and how that decreases with more enrichments used and more discretized points. So also, finite element methods are really useful when solving problems that are defined on quite complex geometries. So the next technique we used was spectral methods within the PGD as well. And these are global methods that can generate high order approximations. So while the finite element method was really useful on those more complicated geometries, the spectral method can obtain a greater accuracy for problems defined on more simple domains. Spectral methods use a basis constructed from orthogonal polynomials. So these could be Legendre or Chebyshev polynomials, and in our work we look at the Legendre spectral methods within the PGD. So again, I've got the Poisson problem with a given source term F, an exact solution U, and another thing with the spectral methods actually is that the domain in each x and y is from -1 to 1, and the points are discretized using something called Gauss-Lovato-Legendre discretization. So these GLL points, we'll call them. And we can see the error, how it decreases by the 10th enrichment, we've got 10 to the minus 5, so pretty accurate. So we can combine the finite element method and the spectral method in the form of the spectral element method. So in this case, this works by splitting up our physical domain into subdomains, or the elements, and then each subdomain can be mapped onto D, a computational domain, using a transfinite mapping technique, for example, this one given by Xi here. And basically each subdomain is given, is solved initially like on its own, and then we can put the approximations together using continuity of the solution. So yeah, in the diagram, I've just got an example of how your subdomain could be split, or your physical domain could be split into subdomains, and then each one solved using the spectral method separately, and then that's going to form this global matrix system where your A1, A2, etc. correspond to each of the subdomains. So we've got some results from the spectral element method. So for example, again, the Poisson problem. I've got source term F, exact solution U, and we can see from the approximation that these subdomains don't have to be linearly spaced. You can see the GLL nodes are going across in each direction. And then on the right, I've just got a log plot for the L2 error, and how that decreases with more GLL points, as well as more subdomains used. So we've got 2, 4, and 8 subdomains, and that contributes to reducing the error significantly. So now I'll talk about something else, which is incorporated into the PGD. So it's the method of the least squares, and this was first researched in 1970s, and it was found to be really effective where Galerkin methods failed. So it's quite robust and has good convergence. So the main idea behind the least squares method is to minimize the residual of a given PDE or system of PDEs in a carefully chosen norm in order to introduce an artificial energy in the form of a least squares quadratic functional. So there are many least squares formulations in the literature, but we have a few significant advantages of using the optimal least squares formulation that's based on ADN theory. So I don't have time, obviously, to go into too much detail about ADN theory, but basically it allows for construction of functionals which are homogeneous elliptic, and so produces problems which are symmetric and coercive and converge really well. So ADN theory allows us to generate a coercivity estimate that only includes L2 norms, so we avoid any problems with negative index norms. And so in our work, we look at just solving the minimization problem rather than the mathematically equivalent Euler-Lagrange equations. So how can we formulate the problem and implement it into the PGD? We first need to recast our problem into a first order problem with additional redundant equations. And it's important to note that for a given second order PDE, there's not just one first order formulation that you could have. So a slack variable is introduced so that we can use ADN theory. There's just a couple of simple checks that's called making sure that the supplementary condition and the complementing condition are satisfied, and from there we can use this ADN theory and show that the problem is ADN elliptic and coercive. So from there the coercivity estimate is generated, and this leads to the quadratic least squares functional. And in the PGD, the approximate solution is defined to be the minimizer of that functional. So I don't know if that made any sense, but we have a Poisson problem, for example, find our first order system and then show its ADN elliptic, and then we can go to find this J as our quadratic least squares functional. And we've got all those integrals, which basically I just expand and take the partial derivatives, and I get systems that I can put into that PGD and solve the solution. So yeah, these are some of my results. Again, with the Poisson problem, we've got exact solution U and source term F, and I found the error that is the maximum of the absolute value of the difference between the exact and approximate solutions. And yeah, on the right hand side, I've got the error decreasing with more enrichments J and more discretized points N. So we've got them going almost as low as 10 to the minus 4. Similarly, the convection diffusion problem, with this we just have that extra term B, the diffusion term, and this problem is the same, but so our exact solution is the same, but the source term is a little bit more complicated. And yeah, I found how the error reacts when we've got different values for B. So on the left we have B as 0.1. Already the error is not going quite so low, just 10 to the minus 2 almost. And B is 1 in the middle, the error is going 10 to the minus 1. And then, yeah, when we increase B to be 10, the error just goes to 0.75. So clearly, as we increase B, our problem's more convection dominated. And so, yeah, I think over the next couple of months, we're going to look at some stabilization techniques to handle this and improve our results, hopefully. Finally, what I'm currently wrestling with MATLAB over is the least squares PGD for the Stokes problem. So I don't have the perfect full set of results yet. But yeah, I was hoping to by today, but no, still, maybe next week if I see anything. So I just thought I'd show a little bit about the formulation. So we have the Stokes problem and find the first order system, show that it's ADM elliptic, and then work to find that J, the quadratic least squares functional. So a lot of integrals and a lot of variables, and yeah, we again expanded and took the partial derivatives and put them into the PGD to solve. And so far we've got promising results for the first enrichment. So they should be even better for the successive enrichments, I hope. So I hope I didn't whiz through that too fast. It felt very quick, actually. To conclude, we've demonstrated the use of the spectral element method and the PGD in obtaining very accurate approximations for solutions to PDEs. We've discussed the construction and efficiency of the least squares PGD that is based on the ADN theory, as the minimization problem is solved directly rather than the mathematically equivalent Euler-Lagrange equations. And yeah, as I mentioned, in future work, we'll look at implementing those stabilization techniques for convection-dominated problems. And hopefully across the next year, we want to look at a mimetic framework, which uses differential geometry and algebraic topology to solve problems on much more complicated domains. So yeah, thanks for all coming and listening. And if you have any questions, let me know.
Any questions for Layla? Yeah.
What is the mimetic framework?
I don't know yet entirely, but yeah, so it's using like a lot of theories from the differential geometry and algebraic topology so that we can look at problems on, I don't know, weird shapes and things, hopefully.
Like copying new.
It's utilizing the basis functions to satisfy some of the conservation laws identically.
And the generality is the mimetic.
Yes, yes.
Okay.
So it will give you your automatic satisfaction of some of the conservation.
Look like construction.
Yes, construction of basis functions.
Yeah, I think that'll be really interesting.
Any more questions? Anyone on the chat? No, just a comment. I was just wondering, so a lot of the problems you've solved so far, well, all of them are like invariant of time, right? What about time-dependent problems? Can this method be extended there, or do you need extra kind of framework on top of this to handle transients?
Good question. I'm not sure. I don't know. We have to, think about that or look into
Yeah,
it.
because I've worked before in just using method of lines to do transient problems with a spectral method to do with this.
Oh, okay. Well,
Yeah.
actually, Arham's got, you're working across time. Yours is time dependent with what you solve as well. So I think you're using the spectral element method as well. So
Oh, lovely. So Alan's going to give us a talk now on the
so
solution.
we'll talk about that as well.
Perfect.
Yeah.
Excellent. So yeah, if there's no more questions, I can thank Layla again.
Thank you.